Let's go back to the single phase full wave rectifier in case we have an RL load. So let's go to this case. So the application we have here is single phase full wave rectifier supplying an RL load, and we assume that it is highly inductive load. So this is the circuit we are studying. Single phase full wave rectifier uncontrolled. And uncontrolled means we have all diodes. So here we have diode, then we have the same two diodes. Then we have our load is RL. Here is the AC source. This is a jump. So here is positive, negative for the AC source. So here we have positive, negative for V out, I out. Don't forget the naming for the diodes. So we name these diodes as diode 1, diode 2, diode 3, diode 4. And here are the directions: I diode 1, I diode 3, I diode 4, I diode 2. The direction for voltages: V diode 2, V diode 1, V diode 4, V diode 2. And at the source, I source and V input. So this is the circuit we have. And we mentioned that for each circuit, we need to sketch the waveforms. And after we sketch the waveforms, we need to calculate or find an expression for the average and for the RMS. So we start by sketching the source voltage or the input voltage. Okay, so we will use 3 squares as pi over 2. So here is pi, here is 2 pi, omega t, V input. So here we will have peak 0, 0. Here we have negative peak 0 and then peak again. And this will be the sine wave for the input. So this is V max minus V max. Now we need to sketch V out, omega t. We need to sketch I out, omega t. We need to sketch any diode current or voltage. So let's sketch, say, I diode 3. I will pick any value. You should be able to sketch I diode 1 and 2 and 3 and 4. Let's sketch I source. Let's sketch V diode 1. Okay. So I picked I diode 3 and V diode 1. You can pick any current in diode and any voltage across the diode. Now let's see what will happen here. So this circuit, as we mentioned before, will have two states, or will have two cases. One case when diode 1 and 2 are conducting, and another case when diode 3 and 4 are conducting. So this is 1, this is 2. So the first case, when these two are off, and the second case when these two let's make this smaller. So these two are off, and here these two are off. So in this case, when the supply here positive negative, so as we mentioned in the last time, this will be positive going up, and here the negative will be going through this one here down, and the other two are reverse biased. Here in this case we have the supply flipped, so here is negative, here is positive. The negative here will turn this diode on, the positive here will turn this diode on, and the source will see or the load will see same positive and negative, which is the rectification happens. So although the supply here it changed polarity, the source polarity or the load polarity is still the same, and this is the basic idea of rectifiers. So in this case, V out will equal to Vn, V diode 1 equal V diode 2 equal 0 because they are turned off. Now I source will equal to I diode 1 will equal to I diode 2. So as you can see, I source is going through diode 1, going through the load, and going through diode 2, and going back to the source, equal to I out. And here it's a constant value because we are assuming that we have highly inductive load. I diode 3 equal I diode 4 equal 0. This is diode 3. So now we have an expression for all the variables. In this situation here, V out will equal to negative Vn because you flipped. If you do KVL here, okay, so this is V source, you can see that V out plus V source equals 0, or V out equal negative Vn. V diode 1 equal to, V diode 2 equal to V diode, or V diode 3 equal V diode 4, this one is 3, equal 0. I diode 3 equal I diode 4 equal to I out. I source equal negative I out. So here is I out is constant, so I out will go down here into diode 4, and it will go negative in the source. Okay, and it is the same in diode 3. If we need to find V diode 3 in this case, so V diode 3 plus V out equal to 0. So V diode 3 equal to V diode 4 equal negative V out. We can remove this. And we found the same expressions last time. And in this case, V diode 1, here is V diode 1, equals to so V diode 3 equal V diode 4 equal negative Vm, because V out and Vn are equal. So even we can remove this. So we can write it as function of Vn, which is the waveform we have. So here V diode 1 plus V out equals 0. So V diode 1 equal negative V out, and V out is negative Vn. So this is positive Vn. Okay, so we can write down here. So I will erase this equation. Now you know how we got it. So we can write down that V diode 1 equal V diode 2 equal to negative or positive Vn, or negative Vn, positive Vn. So these are the expressions we have. The problem is we need to see when to apply these rules and when to apply these rules. So these rules will be applied when diode 1 and diode 2 are forward, and we will move from here to here. This is a condition when I diode 1 and I diode 2 goes to 0. So the condition for the diode to turn off, that I diode go to 0. So to turn on, it has to be forward, and to turn off, its current has to go to 0. These are the conditions that we follow to move between the two cases. So let's go here. Now when the supply is positive, okay, so when the supply is positive, so we have a positive here, which will make this one forward and this one reverse. And we have a negative here. This negative is matching the negative. So this one is forward and this one is reverse. So here we have diode 1 and diode 2 forward, which means that diode 1 and diode 2 will turn on, and we can sketch V out equal Vn. So we will sketch the same sine wave here, and I out is constant at its constant value I out, because we have a highly inductive load, and I diode 3 during this time, I diode 3 is 0. I diode 3 is 0. As we can see here, I diode 3 is 0. I source equal to I out. So I source equal to I out. V diode 1 is 0. So V diode 1 is 0. Now we will come to the problem here. This is a very important concept. Now at this point here, when the voltage of the input or the output start to reverse, the current is not 0. So you can see here that the current is not 0. You can compare this if we go to our last lecture, and if you look at the current here for the full bridge with R load, now you can see this point here, when the voltage goes to 0, the current goes to 0, and we said as this current goes to 0, the diode will stop conducting here, which is not the case in our example. So in our example, when the voltage is 0, the current is not 0, okay? So what is happening here? Let's see what is happening here, okay? So is I diode 1 and I diode 2 are going to 0, so we can move from here to here? This is a no. So what is happening? Okay, let's see. So this is diode 1 conducting and on, and here we have the load, and here we have also connected diode 3, which is reverse. Okay, so this is the source first terminal, and this is the source second terminal. So I'm sketching the top half of the circuit. Okay, I'm sketching the top half of the circuit. Okay, now this diode is open circuit, and the source is reversing. Okay, so the source is reversing. Why the source is reversing? Because we are here. So when we are here, the source is going negative. When the source is going negative, this diode here is coming as forward biased, and it will start to try to inject the current here. Okay, so this diode will try to conduct. Why it will try to conduct? Because it will become forward bias. Why it is becoming forward bias? Because the supply reversed polarity. Why is the supply reversed polarity? Because we are studying at this instant. Now, this current coming into here will try to go back in this diode, so it will reverse this diode and turn it off. And we call this process commutation. And we call this natural commutation. Or sometimes they name it as source commutation. It is not forced, it is by the source. So when the source, when V source goes negative here, it will make another diode forward biased, and this diode will try to inject the current into the load and into the diode, which will turn off this diode. So diode 1 and diode 2 will turn off if and only if diode 3 and diode 4 are turning on. Okay? So diode 1 and diode 2 will not turn off unless diode 3 and diode 4 are turning on. So we can see, or we can say, that this will end here, and now we will have our diode 3 and diode 4 on. Until here, the voltage will be positive again, so diode 1 and diode 2 will kick in again and they will work. So when diode 3 and diode 4 are on, what we will do, we will apply these rules. So V out is negative Vn, so V out is negative Vn, so we will take this Vn, so we will take this Vn here, but we will reverse it, so we will sketch it reversed, because it's a negative Vn. So here Vmax, Vmax, here is pi, 2 pi. As you can see, it's a full wave rectified. And now I diode, I out will be constant because it's a highly inductive. So I out still constant. I diode 3 equal I out. So I diode 3 equals to I out. Then it will be 0 again. I source equal negative I out. So I source is negative I out. So as you can see, I source is AC, but square wave. V diode 1 is positive Vn. So V diode 1 is the same waveform as Vn. So I will sketch the same waveform here as Vn. So the voltage here is negative Vmax, and the peak inverse voltage is Vmax. So as you can see, when diode 1 is on, its voltage is 0. When diode 1 is off, its voltage is negative. And we never saw a positive voltage for a diode, because this is forbidden. If the diode has a positive voltage, it will turn on, okay? And it will be a short circuit. So if you see any positive part here in your graph for V diode, you did a mistake. And this will be the waveforms. Now, if the inductance was just a high, not infinite, not highly inductive, so you should just sketch I out to be something like this. This will be I out. So in this case, if R is not infinity, okay, so the current will increase, then it will decrease, then increase again. So when you sketch here I diode, this case here, this current, you should sketch this part of the wave, and so on, okay? So this is the only difference between highly inductive and inductive, that the shape has some oscillation or it is a straight constant. Also, don't forget, if you apply KCL at this circuit here, I out equal to I diode 1 plus I diode 3. So you can, if you have I diode 3, you can sketch I diode 1 by saying I diode 1 equals to I out minus I diode 3, okay? So you can say I diode 1, so So you can sketch I diode 1 as I out minus I diode 3. So I diode 1 plus I diode 3 equal I out. So if you take I out and subtract I diode 3, so I out here is a square wave minus 0, it will give us a square wave. Then it is I out minus I out, this will give us 0, and so on. This is I diode 1. Also, you can apply KCL here. This is I source, this is I diode 4, and this one is I diode 1. So you can say I source equal to I diode 1 plus I diode 4. So you can get I diode 4 as I source minus I diode 1. So we can go down here and sketch also I diode 4 and so on. So these are how we can sketch the waveforms. As you can see that the voltage waveform is the same as what we got last time. So we can say V out average equal to 2 V max over pi, and V out RMS equal to V max over square root 2 as we did last time. The only difference that I out average equal I out, because I out is constant. So if you look at the waveform for I out versus time, it is constant at I out. And if you take this waveform and you get I out average, it will be I out. And if you get I out RMS, it will be I out. So if the waveform is constant, its RMS will equal to its average. So I out is constant. So I out is constant equal I out average equal I out RMS equals to V out divided by R, V out average. And V out average is 2 V max over pi. So we can find an expression for I out average or I out RMS because it's the same value. Okay. So we are done with RL load. If we have RLE load, so we treat RLE load as highly inductive. So when we are sketching the current I out versus time, it should be constant. The only difference between RLE and RL, if you look at the load here is V out. So V out equal VR plus VL plus E. So this is VR, VL, this is E. So V out average equal to VR average plus VL average plus E average. So this bar here means average. VL average is 0. This is a rule. The average voltage across inductor is 0. And I capacitor average is 0. So this is the rule for inductance and capacitance. This is a stability rule. And IR average or VR average is I out average multiplied by R, and E average is E because E is battery, it's constant, equal V out average. So I out average will equal to V out average minus E over R, and we wrote this expression last lecture, and this is the expression for I out average for RLE load, which is the most important load because this is a DC machine. So the DC machine is actually an RLE, the armature of a DC machine. And this I out average is I out RMS. It is the RMS current. So for RL only, it is a special case of RLE with E equals to 0. So if you put E here equal 0, you can find that I out average equal I out RMS equal V out average divided by R, which is the same expression we used here. So this is the second type of load, or the last type of load, which is RLE load. Now if we go back to our homework that we left last time, if we have an AC source and you have a diode and you have a current source here, 2 ampere, which is equivalent to have RL, and this L is highly inductive. So a highly inductive load, it will have a constant current, okay? So this is a constant current, which is equivalent of having a current source. So the RL is the same as having a current source. Now if you sketch here the input voltage, so the input voltage is a sine wave, Vmax, negative Vmax. So when the input is positive, the diode will be on, this diode will be on, which will have V out equal to Vn, V out equal to Vn, and I out omega t, omega t, omega t, pi, 2 pi, and I out is constant because we have a current source at 2 ampere. So at this point you have current, so the diode cannot turn off. So diode cannot turn off as I diode is not 0, and there is no other diodes conducting in the circuit to take care of the current, which means that the diode will continue on, and your output voltage will continue to be the full sine wave. So this is V out, okay? And in this case, V out average will equal to 0 because you have an AC output, and they call this failure of commutation. Your commutation from AC to DC failed. So in this case, it will not act, it will not work. So your V out is the same as Vn. It is the same sine wave with 0 average. So your output voltage is AC, and this diode is useless. It's just a wire because it will never turn off. So how you can resolve this? How you can solve this? So if you have a rectifier, single phase half wave rectifier, and you connected this to your DC machine, which acts as highly inductive load, the DC machine will not run, because actually this diode will be always on and the voltage here will be AC, not DC. How you can resolve this? How you can resolve this issue? How you can get yourself out of this issue? So the solution is very simple. So the solution is just adding an extra element, adding a diode here, an anti-parallel diode, an anti-parallel diode, or they name it as reverse diode, or the well-known name is freewheeling diode. Now look what is the impact of this diode. When the supply is positive negative, positive here will make this one reverse bias and when this one forward bias. And in this case, so when V source positive, the first diode will be on and the freewheeling diode will be off, and here is your source. So in this case, V out equal V source, and the current is going through the diode. Now when your V source start to reverse to be negative, as we did in the full bridge, so here will be negative, here positive, so this diode here will be reverse biased, so it will be open circuit. So the diode here will be open circuit, and this diode will be reverse bias, sorry, forward bias, because we have, so this one was conducting, so this negative will go here, making this diode here forward biased. So this one will start to conduct, injecting current in this direction. This current injection in this direction is opposite to the direction of the diode, so this diode will turn off, and this 2 ampere is now have a path to circulate. That's why we call this freewheeling diode. So instead of having the 2 ampere going through the source into the load through the diode, the 2 ampere will keep freewheeling into this diode. And in this case, V out will be 0. So if you look at this graph here, I need to know how to copy directly. So if you look at this graph here, now when the supply voltage start to reverse bias, the freewheeling diode will turn on, disconnecting the main diode. So the diode will be on up to this point, then at this point the freewheeling diode will conduct. And when the freewheeling diode will conduct, your V out will be 0, because the freewheeling diode here is shorting the output. So this negative part will be removed. And this part of the current is carried by the diode, and the other part of the current, this part of the current, will be carried by the freewheeling diode. So the freewheeling diode will take care of the current during the negative cycle. Now if you look at this waveform, this is a half wave rectified V out, which is DC. So in order to make your circuit independent from the load, you sell the rectifier like this. So this is the rectifier. So you add this freewheeling diode. So if the load here is highly inductive, which means it will act as a current source, you still have a successful commutation and you don't have a failure of commutation. And this was the circuit that I left last time as a homework for you.